Okay, class, these are the important formulas to know for polar. Polar to rectangular conversions, x equals r cosine theta and y equals r sine theta. For rectangular to polar conversions, tangent theta equals y over x. R squared equals x squared plus y squared. Slope of the tangent line for a polar curve, dy over dx equals dy over d theta over dx over d theta. Many times these questions will phrase in terms of d theta, and that's okay because all you do is divide the dy in terms of d theta over dx in terms of d theta, and these two will cancel out. The area equals 1/2 of the integral from the lower bound to the upper bound of r theta squared d theta. The arc length is the integral from the lower bound to the upper bound of the square root of r of theta squared plus r prime of theta squared d theta. This is how to graph in polar. Our first example, the question is identify the curve by finding a Cartesian equation. This curve is rather simple. It is simply r equals 2. It asks, since we are using r equals 2, we have to use the conversion that involves r into x and y, and this is the equation. Thus, you just square both sides and you get r equals the square root of x squared plus y squared. So 2r equals this, which equals, square both sides now, x squared plus y squared equals 4. And now this is the equation for a circle centered around 0, 0 with radius 2. These are the slopes of the polar equations. Example 2 asks us to find the slope of the line tangent to the curve at the point specified by the value theta. It gives us the curve r equals cosine 2 theta and theta equals pi over 4. Now, in order to do this, we have to convert it into Cartesian. Using our formulas, we do this, and it's simply x equals cosine 2 theta times cosine theta, and y equals cosine 2 theta times sine theta. Now, in order to find the slope, we have to use this formula, and we find the derivatives of each in regards to theta. And simply, the derivative is y prime over x prime, and so you put this in the numerator and this in the denominator, and it asks us to the point specified by value theta, so we must find this at theta equals pi over 4. When you plug that in, you get 0 plus essentially negative root 2 over 0 plus negative root 2 again. The slope is 1. This is how to graph polar equations. Example 3. Sketch the following polar equation, r equals cosine 5 theta. Now we first want to graph the Cartesian form of this equation. This is because it is much more efficient and quicker than directly inputting values for theta. It gives us a continuous line. And so from this we can directly go to polar, and whereas this goes from left to right, this goes counterclockwise. And as you can see, if you just trace this line, you start at 1 and then you go into 0 and then you go back to negative and then you go back and forth and back and forth. And eventually you get 5 petals. A tip, cosine is always going to have the number next to the theta if it is odd as the number of petals. Sine theta also applies. This is the arc length of a polar graph. Example number 4 asks us to find the exact length of the polar curve, r equals 3 sine theta, bounded from 0 to pi over 3, including 0 and pi over 3. Now the equation for the arc length is the integral bounded from the lower to upper boundary. In this case, it's 0 to pi over 3. And it's the integral of the square root of r squared plus the derivative of r, also squared, d theta. And r is given above, and d theta dr over d theta means that we have to find the derivative of r. So we find the derivative and we plug that into this equation. And so we get the integral bounded from 0 to pi over 3 of the square root of 3 sine theta squared plus 3 cosine theta squared. Now what we notice about this is both 3's are squared, so we can probably take those out. Remember, when they're taken out, they have to be squared. So we take out a 9 from both of these and join these two. So it's sine squared theta plus cosine squared theta. If we recognize this identity, this is simply 1. So we can take this 9, square root of 9, out as 3. And what's left is 1, or the square root of 1, which is 1 d theta. Now everybody knows that 1 d theta is just theta when you integrate it. So it's 3 times theta, bounded from 0 to pi over 3. So that's just 3 times pi over 3 minus 0. That equals pi. This is the area of a polar graph. Example number 5 tells us to find the area of the region that lies inside the first curve and outside the second curve. Now our first curve is r equals 1 minus sine theta. Our second curve is r equals 1. We have to graph both on a polar graph with the techniques that we learned from graphing polar graphs. And the first curve is 1 minus sine theta. We'll recognize that this is a cardioid. And r equals 1 is just your standard circle with radius 1 centered around the origin. Now the area formula is simply with the 1/2, and then you have to square r on the inside. And so with that, we take 1/2 out on the bounds from pi to 2 pi. Because if we take it from pi to 2 pi, we can find this shaded area. Not everything is shaded, so we only have to take it from pi to 2 pi. And so once you factor this, you get a positive sine squared theta minus 2 sine theta plus 1 minus 1. That reduces down to sine squared theta minus 2 sine theta d theta. And so you notice that you can reduce this with power reducing formula, and after that you get to take 1/2 out again. So you take 1/2 out again and you get 1/4 on the outside, and inside, since you took out 1/2, you have to multiply this by 2. And you are left with, after integrating this, which is simple to integrate, you are left with 1/4 times theta minus 1/2 sine 2 theta plus 4 cosine theta, bounded from pi to 2 pi. Now if you plug these in, the answer is 1/4 pi plus 2. These are the common mistakes and tips that people make when they graph polar, or when they work with polar. Oftentimes, people assume that the boundaries are always automatically from 0 to 2 pi. However, they are often different, just like the examples that we did today. Always verify the boundaries. Also, many times, people forget the 1/2 on the outside of their integral for the area function. Remember the area function, it has the 1/2 on the outside and then r of theta squared on the inside. And last but not least, watch out. Here's a tip. When you have two graphs overlapping and you want to find the overlapping area for some of these, many times if you have a curve like this, you're not just going to find the area underneath here with this single shape subtracted by this, because it's not going to be accurate based off of the boundaries you use. Many times you have to draw an extra line, and then you have to integrate from those boundaries and work accordingly. If you don't do that, many times you'll be missing or have extra area in your answer. So for problems when you divide two graphs by one line, the boundaries will commonly be different for each shape.